Hey everyone, welcome back. Professor Hank here. So today we're going to talk about a new data structure, and that's going to be the queue data structure. We'll talk about what it is, we'll talk about some practical applications for it, some use cases for it, and we'll go through the algorithms for interacting with the queue. We'll look at Enqueue, DQ, we'll look at a is empty algorithm, and we'll also look at a peak algorithm and a clear algorithm. So we'll define an interface for interacting with this data structure. And finally, we'll discuss the performance characteristics of this data structure. So let's go ahead and get started. So, what is a queue and what is it useful for? So, a queue is what's known as a first in, first out data structure, or FIFO. So, first in, first out. So, real world examples of a queue are basically lines, right? So, when you have a line at the grocery store or you have a line at the bank or an ATM machine or something like this, the first person in the line is going to be the first person that gets out of the line or that gets help or that gets serviced. Now, there's lots of practical uses for this in computer science, computer programming. One is scheduling algorithms. Another is algorithms for dealing with internet protocols. Anytime that you have data that has to be processed in order or that needs to be processed in order, you're going to have a situation where a queue can come in handy. So let's talk about some of the things we're going to need to have in order to implement a queue. So we're going to need to have a node, and that node is going to store some piece of data as well as a reference to itself. So we can represent that as a box like this, and we're going to have two parts. We're going to have a next part, and then we're going to have a data part. So call that, say, X. So there'll be a part of the node that is defined as next, and then our data part, which is X. So if this was in Java, then you could use a class to define this. So class node, and then you'd have, maybe in this case, we're just doing integers, right? So you'd have int X, and then you'd have node next. Okay, and if this was C++, then you'd have a class as well, or you could use a struct even. So let's say struct for C or C++. You'd say struct node, and then you'd have the data that you're storing, and then you'd have a node pointer called next. Okay, so you can implement this in many different languages, but those are some examples, and we're going to represent our node using this box here. Now, in addition to having a node, we're also going to have two references if we're talking about Java, two pointers if we're talking about C++, or two variables if we're talking about Python. So we're going to keep track of the front of our queue and the back of our queue. So we'll create a reference that we'll refer to as F and one that we'll refer to as B. And we'll know that our queue is empty when both of these are set to null. And we'll use 0 to represent null. So this is an example, this is an abstract example of an empty queue. This is empty when both the front and the back refer or point to null. Now, a non-empty queue could look like this. We could have a whole set of nodes containing a whole bunch of data. And we would have our front reference and we'd have our back reference. And that back reference, referring to that last node in our queue, is going to be what helps us to keep this a very efficient structure. We're going to find that all of these algorithms that we're going to learn, they all execute in big O of 1 or constant time. So if we had, say, the values 8, 6, 7, 5 in our queue, then 8 would be the first that comes out because it's at the front. And if we were to add a new value, say 3, then we would have to add it to the end, and we'd have to update our back reference. And then when we remove someone from the queue, then we have to update our front reference, which will cause that front node and that front value, that first value in the queue, to be removed. Okay, so let's look at our first algorithm for interacting with the queue. And this is going to be what we call Enqueue. So this is our Enqueue algorithm. That just simply means to place something into the queue. So our algorithm is going to need to have three pieces of information in scope. It's going to need to have the front reference, the back reference, and then of course whatever value or values we want to store in our queue. So that is going to be the start of it. Now, our front reference and our back reference for an empty queue are both referring to null. Now, when we want to enqueue something, we're going to have to start off by creating a new node. So we'll have a temporary reference, n, and we'll create that new node. So that's going to give us something that looks like this in our abstraction, in our abstract description. And then we're going to have to assign to it the value we want to store. So that value would go right there. And then we're going to have to set its next to null. Because when you're enqueuing, you're always going to be adding an item to the very end of the queue. And that's what is going to cause us to have this first in, first out action, because DQ is going to take stuff from the front and Enqueue is always going to place stuff at the back. Okay, so there's two possible situations with our queue. Either it's empty or it's not. Now, if it's empty, we're going to behave in one way. And if it's non-empty, we're going to behave in another. And that has to do with updating our back reference. So we can test if it's empty by simply checking the front reference or the back reference. You could use either one because remember, this is empty, right? So either the front reference or the back reference we're referring to. No, I'll just use the front reference because I feel like it. I could just as easily have chosen to use the back reference. So if the front is set to null, then what do I need to do? I need to have the front reference change to point to our new node, and I also have to have our back reference point to our new node. So we have a queue that's got one thing in it. And so both the front reference and the back reference are referring to that one thing because the one thing in the queue is both the front and the back of the queue. There's only one thing in it. So all we have to do is something like this. Set that front reference to our new node whose memory address is in that temporary n reference, and set our back reference to n as well. So once we do that, we now have both of our references referring to the correct location. Okay, so that's the first scenario. Now, what about the second scenario? The second scenario assumes a non-empty list. So if we were to do another enqueue operation, we would be creating a new node, just like before. So let's go up to our algorithm. Our new node gets created. We've got a temporary reference n that gets created. We set the data portion of our node to the new value. I'll call that v sub 1. And then we set its next to null. So then we do our test if the front reference is set to null. And in this case, it's not because it's now referring to this node right here. So we have to kick down to our else. So what are we going to do? So what we need to do is we need to update the existing nodes next, the back nodes next. So we're going to do b next set to what? Set to the memory address in that temporary n reference. So b next is the next portion of our node, of our last node, and we're going to overwrite it with the contents of our n reference. So our picture changes to this, which places our new node at the end of the line, at the end of the queue, which is what we want. But you'll notice that our back reference is now out of date. It's no longer pointing to the last node in the list because we added a new node to the list. So we just have to set b to our back to what? To our new node. So we could do either B set to N or B set to B next. And that's what I'm going to do. I'm going to do B set to B next. So what does that do? That overwrites the contents of our B reference with the contents of the next in the node that B is referring to. So that's the memory address of our new last node, our newly created node. So our picture changes to this. Okay, algorithm's over, and our temporary reference goes away. All of our links preserved? Yes, because we start from the front, following the links. We go from the front to the first node, and then we follow its next reference to our next node here at V1. So we go from front, and then we follow the next, and then we follow that last node's next to null. So all of our links are good. The back reference is referring to the last node. Front reference is referring to the front node. That's exactly what we want. So let's see it one more time. Let's add one more node, and then we will do some analysis, okay? So let's look at our algorithm. We create a new node and assign its address to a temporary reference n. So something like this. We assign a value to it. So we'll call that v sub 2. We set its next to null. Once that's done, we check to see if our list, our queue, is empty by checking the contents of the front reference. And it does not contain null because it's got the memory address of that first node. So we skip down to the else, and then we update B next to N. So what's B next? That's this right here. And we overwrite the contents of that reference with the contents of the N reference. What's in the N reference? The memory address of our V sub 2 node. So our picture, our abstraction, changes to this. And then we set B, our reference B, to B next. Now what's in B next? The memory address of our new node. So our picture changes to this. Temporary reference goes away, and we're left with a queue where the front reference points to the front node. That node points to the node that follows it. That node points to the last node, and the last node refers to null. Our front is pointing to the front, or referring to the front node, and our back reference is referring to the back node. So everything is working just great. So our algorithm is solid. Now what we want to do now is we want to do some analysis on the efficiency of our algorithm. So we want to talk about big O is what we're doing here. We want to see how it performs in the worst case. So let's count some operations. So we're creating ourselves a new node and assigning its memory address to n. We're assigning the value to our new node. We're assigning null to the next. Now we're going to have a test no matter what, no matter how many nodes there are, we're going to have a test. So that's going to be testing the contents of that front reference. So if it's true, then we'll have an operation here and an operation here. If it's false, we'll have an operation here and an operation here. But we're not going to have both of them. So it's either or. So it's either going to be these two operations or these two operations. So we'll take these four that will happen no matter what up here, and then we'll add the two that'll take place if either of these execute or either of these execute, right? So that would be 6 total operations for a total performance of big O of 6, which is constant time, which means that we can rewrite it as big O of 1. Now you'll notice that the number of operations doesn't change based off of how many nodes there are on the list. We've got 3 nodes in our list right now, in our queue right now. If I add another node to it, here's one operation. That's creating the new node. That's 1. Assigning the value. That's 2. Assigning next, null. That's 3. Doing our test. That's 4. We're testing the contents of F. So we skip these guys right here and we kick down to the else. So then we set B next to our new node. So that's another operation. And then we set B to B next, which is another operation. So this back reference is really, really helpful, right? So that's 6, which we can rewrite as 1, big O of 1. So it's really, really useful, right? So this back reference allows us to avoid having to traverse the entire list to find the last node in the list, in our queue, the place where we would have to add our brand new node. So there's always trade-offs when it comes to computer science and computer programming, trying to figure things out. Here, we're producing a much faster algorithm by using a little bit extra memory. We can avoid a loop by spending 8 bytes for our back reference.